I think you will all understand the structure of the planning graph now. You know what types of node exist in the planning graph, proposition nodes and action nodes, and you know what types of edges exist between these different types of nodes in the different layers. And in the example graphs we've looked at, you should have seen that we can grow this planning graph in my illustrations left to right, starting from the proposition layer P0, which contains those propositions that are true in the initial state. The process of growing the planning graph is what I call forward planning graph expansion, and that's what we will be looking at next. One of the issues with the planning graph is that it is really an infinite graph, because I've never told you where we need to stop generating action and proposition layers. So in theory, this sequence could just go on and on. This proposition here tells us when we can stop expanding the planning graph and do something else instead. Suppose we are given a propositional planning problem consisting of the usual components, and we start generating our planning graph consisting of node and edges, nodes being the usual proposition and action layers. Then the following must be true. If our goal that is part of the given planning problem, the goal G, is reachable from our initial state, then there must be a proposition layer, let's call this layer PG, for which the following holds. The first is that all the goal conditions must be a subset of this proposition layer PG. So if PG was a state, then our goal would be satisfied in that state. And the second thing that must be true is that there does not exist a pair of goal conditions that are part of our goal. There does not exist such a pair, G1, G2, that is mutually exclusive in this proposition layer. So, not only are all the goal propositions in this layer, but they can also be achieved together, at least as far as we know. One caveat here is that this only works in one direction, so this direction. That means we still only have a necessary condition for when a planning graph may contain a solution. But we can exploit that, and we will look at how to do that next. And here is the basic idea that underlies the graph plan algorithm. We start by expanding the planning graph just as we've seen it so far. So we start off with the initial proposition layer, and we know what this contains. And then we expand the graph in each step by one action layer and one proposition layer at a time. So this is our first loop that we go through to expand the planning graph. But we don't want to go through this loop forever, so here's the condition when we have to stop. Namely, from the first graph, which contains a layer PG, for which the proposition we've just seen gives us a criterion that the goal may be satisfied and the plan may be contained in the graph. So we have to check whether all the goal propositions are true in the last proposition layer that we've just generated, and whether any of the pairs of goal conditions are mutex in that proposition layer. If and when we find such a layer that contains all the goal conditions, none of which are mutex, then we can stop or at least interrupt our planning graph expansion and do something else. And that something else is a backward search in our planning graph. So we start from our last proposition layer and search backwards towards the layer P0 to try to extract a plan. And how exactly that is done is something I will explain to you later. All you need to know now is that this search can fail. So that means we haven't found a solution plan in our planning graph. And in that case, what we do is we go back to our first step and we continue to expand the planning graph. Again, we add another action and proposition layer. This will, of course, contain our goal propositions, and they can't be mutex anymore. And then we can search backwards again in our graph that contains those additional two layers now, and so on, until we find a solution plan. And for those of you interested in the implementation details, here is the data structure that can be used to hold the planning graph. Specifically, we're talking about the structure that can hold the kth planning graph we're generating, which consists of the proposition layers P0 through Pk and the action layers A1 through Ak. And the first graph we generate is, of course, G0, which contains just the proposition layer P0 and no other layers. For quick access, the proposition layers and action layers can be stored into arrays, and the symbols within these layers should be stored in sets of proposition symbols and sets of action symbols. They should be represented as sets because we don't want the same symbol appearing twice in the same layer. In fact, since we know that proposition and action layers are monotonically growing, we can store each symbol in only exactly one layer, and we know that this symbol must also be contained in all the following layers of the same type. And then we have the edges of the planning graph. In fact, we have 5 different types of edges, all the ones we've seen before. So there are precondition edges going from proposition layer pj-1 to action layer aj to the following action layer. We have positive and negative effect links, which connect the action layer aj to the following proposition layer pj. And then we have mutex relations. They are the proposition mutex links that are within each proposition layer. And we have action mutex links that are within each action layer. The only thing that is remarkable here is that our mutex proposition links start from index 1. That is because in our proposition layer P0, we don't have any mutex relations, of course. That is an initial state, it's consistent, and therefore nothing in it can be mutually exclusive. So that's the data structure. And here is the pseudocode that describes how we can expand a given planning graph with a new action and proposition layer and all the links we need. So we assume that we are given the planning graph gk-1, and we want to generate the planning graph gk. Then we start by generating all the actions we need in our new action layer, which is ak. And in this action layer, we find all those actions that have their preconditions in the preceding proposition layer and that don't have a pair of preconditions p1, p2 that are mutually exclusive in the preceding proposition layer. And when we've got our new actions, we can compute the mutex relations between our new actions. And we can do that by going through all the pairs of actions that are in our new action layer. They must be different actions, and use the mutex function that we've described earlier to compute whether they are mutex in our new action layer. Then we can compute the next proposition layer, pk, and that simply consists of all the positive effects of all the actions in our preceding action layer. Note that we don't have to explicitly carry forward the propositions from layer pk-1 because we have the no-op operations doing that for us. Next, we compute mutual exclusivity between the propositions in our new layer, and again we have to go through all the pairs that are different and use the mutex function for propositions that we've defined earlier. And now all that's missing are the precondition and effect links, and what we do is simply go through all the actions in our new action layer and add the corresponding links between the correct nodes. And these are all listed here: preconditions, positive effects, and links for negative effects. And that's it. And here is a proposition that states what I've already mentioned a couple of times, namely that the complexity of expanding the planning graph is polynomial, and therefore it can be done reasonably fast. And what the proposition states is that the size of the planning graph up to level k and the time required to expand it to that level are polynomial in the size of the planning problem. The size of this propositional planning problem can be described by the number of propositions and the number of actions we have in this problem. So we assume we have n proposition symbols and m action symbols. Then we know each proposition layer is a set of symbols, so each proposition symbol can be contained at most once, which means the size of each proposition layer can never be more than n. Similarly, for the action layers, they contain at most all the action symbols plus all the no-op actions, and no-op actions, of course, we have n for n proposition symbols. So the size of an action layer can never be more than n plus m. And when you go back to the slides where I explained the different algorithms for expanding the planning graph, I've always explained to you that they run in polynomial time, and that means each layer can be generated in polynomial time. And of course we only have a linear number of layers in our graph gk, or a fixed number k. So the whole algorithm for expanding the planning graphs runs in polynomial time. Now, another important property of planning graphs is that they will eventually reach a fixed point level. And here is what a fixed point level is. A fixed point level in a planning graph is the kth level in that graph, such that for all I that are greater than k, so for all the following levels, they must be identical. So for all the following layers, we have that the propositions in the following layer has the same propositions as layer k. The mutex relations are the same for all the following layers. The action symbols are the same, and the mutex between actions are also all the same. And this holds for all the layers following the fixed point layer, not just for one. And the important thing is, of course, that every planning graph must have a fixed point level k. That is the smallest k for which the proposition symbols in one layer are the same as the ones in the next, and the mutex relations that hold in that layer are also the same as the next. Note that these two proposition layers must be the same if the two sizes are the same. Because proposition layers are monotonically increasing, if they have the same size, they must also contain the same symbols. And the same goes for the mutex relations, which must be the same if they have the same size in subsequent layers. Now, if the two proposition layers pk and pk plus 1 are the same, and the mutex relations are also the same, that means the actions that are applicable in pk are exactly the same actions that are applicable in pk plus 1. So that means the same actions exist in action layer ak and ak plus 1. And if they didn't add any proposition symbols from pk to pk plus 1, then there's no reason why they should add any more from pk plus 1 to pk plus 2, and so on. And the same argument can be made for the mutex relation in this action layer, because this only depends on the preceding proposition layer and on the independence between actions, which never changes, of course. So, once we have reached a level where the number of proposition symbols is no longer growing and the number of mutex relations that are holding is no longer shrinking, that means we have reached a fixed point level, and every planning graph must have such a fixed point level.